All right. Hello, everyone. It's my pleasure to introduce the first keynote speaker of the conference, Max Welling. Max barely needs an introduction, and he has far more achievements than I can discuss here right now, so I'll try to keep this short and give him lots of time for his excellent talk. Max is a research chair in machine learning at the University of Amsterdam and a VP technologies at Qualcomm. He got a PhD in quantum physics under Nobel laureate Gerard de Hooft, and he has authored over 250 papers in machine learning, computer vision, statistics, and physics, including several seminal ones, like the Variational Autoencoder, for example. As a result, he is also receiving more than 10,000 citations a year, and he's done a lot in terms of service. He has been program chair and general chair of many conferences, including Europe's, and he has also received a lot of awards, including the ECCV Kendering Prize and an NSF Career Grant. He co-directs the Qualcomm University of Amsterdam Deep Learning Lab and the Bosch University of Amsterdam Deep Learning Lab. Today, I'm very excited to hear Max talk about combining classical learning, inference, and optimization algorithms with learned neural networks. Please join me in welcoming Max Welling.
Thank you very much, Frank. I hope everybody hears me well. Yeah, I'm very excited actually to talk here at the European Conference for Machine Learning. Note that we just finished the opening of the ALICE units across Europe, 30 of them. And I hope that we build a vibrant ecosystem of machine learning researchers across these units, but also with good conferences like this one. Okay, so today I'll be talking about indeed, as Frank said, using sort of combining deep learning with more classical sort of algorithms and optimization or inference algorithms. And I'll be discussing two sort of design principles, which I call amortization and augmentation. So the overview will be first a little bit of a sort of high-level introduction on why we need generative models and what they are. I'll talk then about what is amortization and augmentation. And then I'll go actually through just a whole bunch of examples that we worked on together. And then I hope to point out sort of the two, in what sense they are either amortized or augmented. So at the very, very highest level, machine learning is basically combining your inductive biases and data in order to make better predictions or to take better actions. And so the amount of data relative to the amount of inductive bias determines what kind of machine learning algorithm you will be using. On the one end of the spectrum, where you have lots of data, let's say in text domain or an image domain or video, deep learning shines. Also, in this domain, typically you have applications that are often restricted, like I want to predict melanoma, that's one particular disease, or I want to segment objects from images or things like that. Now, often when you try to move away from the particular domain that you have trained your network on, your discriminative network on, things start to break apart. And so that's why I think, and many people with me, think that generative models are going to play an important role in machine learning. In generative models, it is very natural to add your inductive biases or your priors into your model. And for instance, causal relationships or physical relationships between things. And because of this fact, the models become far more robust and they can generalize out of domain more easily. Now, what is a generative model? What do we mean by a generative model? And there's actually a very broad class of models, but I would say it is what everybody else does. So it's, the machine learners, they often work with discriminative models and deep learning methods. And in the days before deep learning, many machine learners actually also worked a lot with generative models in the shape of, graphical models. But basically any scientist that you talk to, whether it be an economist or whether it be an astronomer or a physicist, they build generative models, perhaps in the form of simulators or ordinary and partial differential equations and all these kinds of things. So for here you have, and they're remarkably powerful, right? Here's a sort of a a little video of two galaxies that are colliding, and there's only a couple of parameters that may go into this, because the laws of physics basically determine completely how this highly complex sort of simulation will run. And that is the power of generative models. They typically require less parameters, but a lot of inductive bias. So the pros and cons, so you could sort of divide the world in these two models. There is the white boxes. This where we have these generative models. They're very data efficient because we use, let's say, the laws of physics or causality or expert knowledge to build these models, and that's why they often require fewer parameters. They're often interpretable because the variables that we use and introduce and the interactions mean something in the real world. And as I said, they're often better at generalization because if you have the causal model correct, then if you've learned that model in one context, you can then apply it in a completely different context. Now, the black box model is the model that in machine learning we use and have been extremely successful in the form of deep learning. Right? It is a highly flexible model that can be home to billions parameters. I mean, the latest models like GPT-3, I think they have like a ridiculous amount of like hundreds of billion parameters or something like that. And that's the power of that, is that if you have sufficient data, you can go far beyond the limits of the human imagination, right? Because if we want to write down a model, every model is wrong in a way. It's far simplified, and especially when we need to write it down, our imagination can only go so far. But if you have like 100 billion parameters in a model, then you can basically model every little pattern that's in the data. That's why for these domains with lots of data, they are extremely accurate and also very fast. And this is maybe a little subtle, but they're fast also because we are often interested in this direction where you put in the raw data on one end of the system and you predict the properties or the class labels or whatever on the other end. So we run our algorithms in this discriminative direction. Now, if you build a generative model, you often have to invert it. And if you invert it, you have to use Bayes rule in some approximate form, and that is slow, and you introduce errors in that process as well. Right? So there's definitely advantages and disadvantages to both of these methods, and really what we are looking for is a combination of both, hybrid systems that combine both of these sort of advantages. So then, here are the two sort of design principles that I've been using in designing these models. And so amortization is, you could define as finding or generating related problems to learn a model or policy to do X, right? So instead of trying to solve this one instance of the problem, you're going to try to find other problems in sort of a related family of problems, such that you can see patterns, you can learn patterns from all those problems, and you're going to use that inside the current problem to do a better job at either inference or optimization, right? So in the variational autoencoder, this you can think of as learning to infer, right? So instead of performing the inference inside, a particular instance for a particular data point, only for that data point, using perhaps mean field approximations or something like that, what you actually do is you learn a model on the entire data set, and in order to sort of predict what the outcome of the inference procedure would be. And then perhaps you can fine tune it a little bit afterwards. The other class is learning to optimize. So, you have many, if you're trying to say solve a TSP, like a traveling salesman's problem, right? You can hit it with, the most, sophisticated optimization algorithm for that instance. But there may be patterns that you can learn by looking at many of these instances of TSP problems. And then you can sort of learn a policy to tell you what would be the next city to connect to, right? And again, the best systems right now are still these mathematical optimization tools, but there's also advantages to learning to optimize, in the sense that if you would have to do it on the fly, very fast, in the face of uncertainty and all these kinds of things, then in fact, a learned policy could help. And I'm claiming that the hybrid between these systems could actually be very advantageous. And another class is learning to learn. So instead of learning a model by using, for instance, gradient descent, on a single data set, you could say, well, how can I optimize my optimization parameters, like the step size and gradient descent, or maybe the orientation and gradient descent, by looking at a lot of these problems jointly and sort of learning an algorithm that would sort of help me find the best possible update at this stage of the optimization algorithm. That's what we call meta learning or learning to learn. Okay, so that's the first sort of design principle. And then the second design principle is what I call augmentation. And in augmentation, we could define as a hybrid system that combines classical, hand-engineered, or signal processing methods like that with learned machine learning-based models or policies. So you sort of combine a deep neural net, let's say, with a classical sort of optimization tool, for instance. Now, as examples, you can think of, let's say, building a probabilistic program, which is some kind of language to build graphical models, or simulators, plus a neural net. You can wrap a neural net around it, and you can learn the neural network, let's say, such that it will help the simulator to simulate well or something. Or another thing I will discuss is data forcing terms in encoder. So an encoder takes an input and tries to predict, let's say, a latent variable. But if you know what the decoder is already, which is the channel under which you generate your data, perhaps you could use that information about the known channel inside of your encoder to do a better job. And I'll discuss that more later. And then final sort of hybrid inference, methods that combine classical inference, like let's say in graphical models like belief propagation and mean field, with neural networks. And I'll also discuss these more in the context of error correction decoding algorithms. Okay, so there is a whole field that's called inverse modeling, forward and inverse modeling, that is very popular in science. That is highly related to the variational autoencoder framework. And what do people do in sort of forward and sort of inverse modeling? They basically describe a forward generative process of how you generate data, right? And this is typically a known process, like a channel, a noisy channel that you understand. Like, how do you generate an MRI image? It depends on the actual machine that you use, and you know the specs of that machine, and so you can basically describe quite precisely, what that forward channel is, right? So there is, let's say, some image that you want to reconstruct, but you don't have access to. You describe the process by which you observe data, which is, like I said, maybe this blurred or subsampled version. And then you're interested in the inverse model. And the inverse model is take in the observations and perhaps some prior information and try to reconstruct the original model. Now, the variation autoencoder is very similar. So in the variation autoencoder, we have the forward process here on the right-hand side. We call it the decoder, which is you start from some latent image that you don't know. In this case, it's the high resolution 8, and you generate the observations that you see, the blurry 8. Right? And then there's an encoder, which is the inverse model, which takes in the blurry image and tries to reconstruct the high resolution image X. Okay, and we call the forward model Py given X, and the inverse model we often call as Q of X given Y. Now, of course, the variation autoencoder is sort of a prime example of this particular philosophy, and here's more detail about that. So in the variation autoencoder, when we wrote it down in 2014, you have some kind of latent variables P of Z, and you have a prior over these, and you have maybe some class labels, and then there is a neural network that predicts the parameters of some probability distribution P, like the mean and the variance, or some other distribution, maybe the probabilities of a multinomial, and then you sample, let's say, an observation X. So that will be the known channel or the forward direction. And then there's the inverse of that, which is you take your observations, could be the raw pixels of an image, you again push it through a neural net, you predict the mean and the variance, from which you sample, let's say, your latent variables Z, so that's Z given X, and then from there you could predict Y if you're interested in this discriminative model. So in the decoder, you can put your prior knowledge about the generative process. In fact, you could put there a simulator if you wanted to. And in the inverse model, you need to learn that in order to predict the unobserved latent variables. It's very related to EM, if you're familiar with EM, where this part is basically, you infer your unobserved latent, or you impute your unobserved latent variables, and this is the sort of the part, the model itself that you do updates on. But you can also sort of view this inversely. You could say, well, I could actually be interested in this model because I'm interested in doing predictions, and this part of the model I'm going to use as a sort of regularizer. I want my inverse model to be close to the inverse of a known forward model. Okay, the objective of VAE is not super important if you're not too much into equations, but so here is basically it's a KL between the probability of the data, the empirical distribution times the encoder model, and the generative model is the prior over Z and then X given Z. You can decompose these into two terms, a KL between the marginals over X and a KL between, or an expected KL between the posterior, the true posterior and the approximated posterior. And of course that, when you really solve this, it means that your model has a probability distribution which is very close to the empirical distribution, and your variational posterior is very close to the true posterior distribution. Okay, so then I come to that. So I want to say it's clear that this is amortized, right? Because I could have done sort of inference directly on this per data point, and then I wouldn't have a QZ given X, but I would have just a Q of Z. So this is clearly an amortized model. And if I would put here simulator, it would also be an augmented model in some sense. So, but that's the augment. There I had augmentation in the decoder, in the forward model. But now let's take this one step further, and now we're going to do augmentation in the inverse model. So in the encoder model. And this is what I meant by saying data forcing terms. Okay, so the idea is that we have some kind of classical algorithm with which we can do optimization or inference. And typically these algorithms, they have iterations, so they iterate over updates. And at every iteration, you get a better estimate of what you're interested in. So we just think of that iteration as an unrolling of a neural network. So basically as a procedure that we can sort of think of as layers of a neural network. So think of that maybe as a recurrent neural net. So then we're going to sort of add sort of abstract sort of neural network states around it. Now we're going to add some memory states S, just some auxiliary states in which we can store information, right? And so now what we're going to add also is a neural network that is sort of trying to correct the inferences that the classical optimization algorithm is making. And moreover, in that process of making these corrections, it will have access to the forward channel, which is P of Y given X. So note that this is trying to do Q of Z or X given Y, but we know the forward model P of Y given X. And so we should sort of try to use that information during inference. Okay, so how would that work? I'll, of course, go into more detail later. So we have our input data. We have an engineer update, the classical update, to get to a new estimate X that we're interested in. I have some neural network which takes information from the classical update and tries to compute a correction that's learned from data. I have memory states, and I'm also going to inject this class, information about if this were to be X. If I would send it through my forward channel, I would get Y. How does that Y that I generate compare to the input data Y? If it's very different, I have a signal that I'm on the wrong path, and that error I can feed back into my neural network as additional information to sort of try to improve itself. And so here we have the backbone classical algorithm, and the neural network sort of iterates on the fringe of that. You have these memory states that help, and all of this should sort of at the end of this T iterations come up with a better estimate of the thing I want, which is the unobserved variable X. So what are classical solutions to this inverse modeling, right? So the classical solutions are typically of the kind, write down some generative model, P, which this is the channel, which is P of Y given X, and this is a prior, perhaps, over what does a likely solution X look like? And then I'm just going to do gradient descent on this objective. So I'm just going to take, going up on this surface to get to the highest likely X that could have generated my Y, and that is somewhat consistent with my prior. But there's many other inference algorithms which are far more sophisticated than that. And one prime example of that is belief propagation. I have some graphical model. I'll go into an example later in error correction codes. There's some graphical model. There's some variables X that I'm trying to infer, some interaction nodes that are factors that sort of are functions of subsets of these variables. And then I'm going to send messages in this graph in order to figure out what the best estimates of these x's are. And of course, these messages embody the graphical model and embody these factors f, which are in my graphical model or in my forward model, so that they sort of can infer these x's. So that's the classical solution. Now, what does a full sort of deep learning solution look like, right? So the other side of the spectrum, it basically says, well, generate a gazillion points x and y, right? Where x is the sort of unobserved thing, and y sort of x is the thing I want to reproduce, and y is these observations I would find in my measurement device, and then learn an inverse map. Basically, look at all these examples and then learn the map that goes from y back to x, right? So, and for instance, for images, you can use some kind of UNet structure here with convolutions in the middle, where you can take, let's say, a highly blurred image, and the output of this would be a high resolution image, right? But it's completely learned, and as it does this, it knows nothing about the forward models. It knows nothing about the fact that I actually do understand very well how y is being generated from x. All that information has to be sort of implicitly present in these data that I'm generating. Okay, so now I'm going to go through a couple of examples where we applied sort of this strategy of trying to sort of incorporate these things together, and some of them are more detailed than others. So this one I'll just skip over fast, but it's a very exciting application where we use precisely this idea. So in the MRI context, I have, let's say, an image of the brain that I would like to reconstruct. But that's not what I measure. What I measure in my MRI machine is highly sparsely subsampled Fourier components. So you would have to first go to the Fourier domain and then subsample to get to your actual measurements. So that's the forward model. The backward model would go from here back to here. Now, one thing you could try is to say, well, if I were here, I would do an inverse Fourier transform, I would get here, that's clear. But if I have now also subsampled and I do an inverse Fourier transform, I get here. And this is actually a very poor reconstruction. So I need to sort of either clean this up or find some map that takes me directly from here to here. And then it's very easy to say, well, let's just generate a lot of data for this. So let's say, take a reconstructed image where I use a lot of these Fourier components, which are the typical thing that people do. We use a lot of Fourier components. Then subsample that set of measurements, and then try to reconstruct this back, right? Then if I'm very successful at that, the next time I do not have to measure that much. I can use a sparse subset. And that was exactly the sort of the challenge that NYU and Facebook sort of started in the Fast MRI challenge. So we entered in that with what we called a invertible recurrent inference machine, which is precisely one of these unrolled sort of models where at every iteration we try to find a reconstruction of this X, and then we send it through the forward channel to check how well we're doing, and we feed the error signal back in, and then we push again, with some additional sort of memory states, we push it again through a whole bunch of convolutions and all these kinds of things in order to do a new try and get another reconstruction. And we iterate that for t steps, and then we backpropagate through the whole chain. So we had to do this trick of making this whole architecture invertible, because clearly these are 3D images, and there's a lot of feature maps, so the amount of stuff you need to keep in memory is gigantic. And so by making the whole thing invertible, you do not have to store all these feature maps, but you can reconstruct them on the fly as you go backward. Okay, so let's go here's another example where we sort of tried this out. So it's a nonlinear Kalman smoothing operator algorithm. So the dynamical, so the data was generated from this Lorentz attractor, which is you probably know these pictures. It's kind of a chaotic nonlinear dynamical system that's described by this ODE. And again, if we sort of apply the strategy that I just explained, if we take just the observations, it looks like this. These are noisy observations. If we train a graph neural net, I'll talk more about that in a minute. If we train a graph neural net, we get this. It's quite hard to train. If we take an extended Kalman smoother, which is the opposite side of the spectrum, which doesn't use any neural network, we get this. And if we do the sort of combined strategy, we get very good results. If you look at the particular, plot, here's the number of samples that you use in order to train your model. Here's the error. And you see that, of course, when they have very few examples, then the Kalman filters that know, at least approximately, know the forward model and just do inference in that, they do fairly well, much better than a completely learned model because there's so little data around, right? But as you add more data, these Kalman filters will not improve anything because they're not learning anything. And the graph neural net, it will start to improve to become better than the Kalman filters. So you can learn to do inference if you have enough data. But the hybrid methods that we developed, they are still much better than either of these solutions at any point on the spectrum. Okay, so for this, I will go into a little bit more detail to just give you a sense of how you build these systems. So the problem that we're trying to solve here is a low density parity check code. And that's basically, you have an image, you add some redundant bits. So these bits basically are called check bits, and they sort of do the sum of 3 bits in the message that you want to send mod 2. So so they sort of encode some redundant information in this image. So then you send them over your noisy channel, your decoder, and then you get this here. So it's now noised up because some bits had a certain probability of flipping. And then the task is to take this and reconstruct the original image. So we're interested in this part. So here you can actually see the algorithm at work. It's a low density parity check code. These things are actually used in sort of wireless communication, and then you can actually get, perfect in this particular case if you're below the sort of the Shannon limit. Okay, so how does that work? So in this case, the algorithm that is really competitive, that does that inference, the classical algorithm that we're going to build around, is what this is called belief propagation. So the factor graph looks like this. So here are the variables that we are interested in. And then we have some of these parity check bits, which sort of sum up 3 bits, mod 2. And then there's these factors, which is basically the information that you receive over the channel. This is a continuous signal that is basically acts as a bias to either 0 or 1. Okay, so then in order to find these bits, you sort of initialize them randomly, and here are these factors, and now you run belief propagation on these edges, which basically means you basically unroll, if you want, this particular, well, forget that. So let's say you basically take the edges of this graph, right, and then you send a message from one node to a factor, and from a factor to a node, and you keep on doing this even though this thing is loopy. You're going to keep sending messages, around, and they can run in circles, but that's okay. It's an approximation. And as this thing converges, if it converges, then you'll get, a very good estimate of the probability that the bit is either in 0 or 1 position. So the messages are, maybe complex in this case, but it's basically you multiply messages together, and you have to sum them over these factors. And then when you want the probability at a node, you'll again multiply all the messages together and you normalize. Okay, so that's augmented belief propagation. So how are we going to add a sort of a neural net? How are we going to wrap a neural net around this classical algorithm, right? Because we want to do augmentation. So the idea is to notice the similarity between belief propagation, which is a message passing scheme over the edges of the graph, and a graph convolution. So a graph convolution, basically any convolution can be seen as sending messages on a graph. So if you have a normal convolution like this, then basically you can think of it as the center node receives messages from the neighbors in the graph. For a normal convolution, all these messages can be different. So the matrices that are multiplying these features on the neighbors can all be different. But for a graph convolutions, we typically take these neighbors to send the same message. Well, it's not the same message, but it's this feature is multiplied by the same matrix. And the reason is that, there is no ordering in these nodes. So I could just move this particular node here, and it would still be the same graph. And if I don't have a definite ordering, I don't want the outcome here to be dependent on the ordering. So if I use the same matrix, then clearly in whichever order I send, I treat these messages in my computer, I will get the same answer here. Note that the message that you send to yourself can actually be different. Okay, so then the GNN, in equations looks like this. So we have a message that goes from a node to an edge. It's basically some nonlinear, say, neural network type of function that takes in the feature on one node, the feature on the other end of the edge, and then there is some additional information, side information that you can feed into that neural net. That will give me a message from I to J. That sort of lives on the edge. Then, in order to send a message from the edge to the node, I collect all the messages that are now on these edges. I sum them up, and then finally, if I've summed them up, I'm also going to send them through a nonlinearity, perhaps with some additional side information on that node A, and also depending on my sort of the information, the feature vector that's living there. And that will give me my new H at that t+1 at that node. Okay, so that is also a message passing algorithm. So now the idea is to try and combine these. Now, in order to do it for LDPC, I need to go through one detail that you can sort of forget if you're not interested. That is actually, we live on a vector graph and not a normal graph. And the point is that on a vector graph, you need more messages. You have messages from nodes to edges and edges to nodes, and edges to variables to vectors and vectors to variables. And so you have to sort of do a little bit of work to map the normal GNN update to a vector graph update, but it's not rocket science. It's basically you take these factors and you treat them as additional variables. It's not too important. So it's easy to do it, and that's all you need to remember. But then this is kind of the more detailed picture of how we would implement such a system. And okay, so we are doing this. This is an inference network, so it's an inverse model. You take the observations Y, and you're trying to reconstruct at the end X, the latent variable X. So this is an encoder model. So we initialize it with some latent variables for the RNN, and we have also some initial messages mu, which are the things that the belief propagation algorithm pushes around. So then I do one update. Let's go here. So I do one update of belief propagation on all my variables. And that will give me the messages from vectors to nodes and nodes to vectors. I'm going to feed that information into my graph neural net. Now, my graph neural net had these context variables A, and that's where I will store these messages that I receive from belief propagation. It will do a learned update on the graph, on the same graph, a learned update on my graph neural net. It will then produce a correction for the belief propagation. So it will produce a correction term that will nudge the belief message to be slightly different. So this feels a bit similar to, let's say, learning to learn, where you would have a gradient update and you would nudge the gradient update to do something slightly different, maybe make it a bit bigger or turn it a bit left or something like this. So then we have, and then we go to the next iteration. We have our messages, we have our internal state of the RNN, and then we move to the next. So we do this for a couple of iterations, and we arrive at X. We know ground truth because we have generated lots and lots of, data where we know the actual message that we wanted to send, and we have the noisy channel. So we have, we can sort of train this model, and we back propagate through the whole chain to, of course, the parameters here are shared, like you would do with an RNN. And you would train up your graph neural net update, right? You would train it so that the belief propagation and the GNN together will give you the best results. Now, this is a prime example of both augmentation and amortization, because it's amortization because I'm training a network that goes from Y to X. It's augmentation because I have a classical algorithm and a neural network algorithm join forces to get the best out of both worlds. Okay, if you actually again, it's the same story as I showed you for the nonlinear dynamical system, right? So if you look at the classical algorithms, which are the LDPC codes on a bursty channel, so all these LDPC codes, they are trained for Gaussian channels, but they're not working necessarily very well for bursty channels. And the bursty channel is that so now and then the variance of the channel goes up because maybe something is in front of the channel or something like that. So you can simulate that by so now and then adding, increasing the variance of the model. And you can do your LDPC code as you add more of this variance, if you add more of this burst, then the LDPC codes will start to deteriorate. And even the LDPC codes designed for bursty channels will deteriorate a lot. If you go to the GNN, the learned model, in this regime is really bad because the LDPC code is designed to do very, very well for this sort of low, for this channel, because it's designed for this channel. But if you increase the burstiness, at some point the GNN will overtake the LDPC codes. Now, the hybrid system that we developed is better for any value of sigma, and so sort of, it sort of represents the best of both worlds in that sense. Now, there's a couple of more examples I go through. I have 10 more minutes, so these might go a little fast. If you don't understand all the details, that's fine. Just try to get the high-level idea. So there's this other problem in wireless communication, which is called MIMO detection. And that's basically when you connect with your phone to a base station in order to sort of transmit a signal. So there's this, you're the transmitter, there's a whole bunch of users that connect with their phones, and then there's the receivers, which is these base stations which receive all these messages, and inside one of these base stations there's many of these antennas. And there's all these channels that go from users to each one of these receivers. And of course here the idea is again to try to reconstruct or demodulate the actual message that was being sent from the user and then send it over the channel. So again, we do a similar thing. We call this re-MIMO, where we have again an iterative procedure, an unrolled classical procedure if you want. So in this case, there's not much of a classical solution, I think. But we do inject the noise, the information of the channel. So the information of the noisy channel that we know is in this P of Y given X. And we do infuse that information into our neural network. So here are two sort of neural networks that we train in order to do the reconstruction. So basically think of it this way. Every time I do a reconstruction, I can push it through my former channel, figure out what the data would have looked like if that were the actual sort of reconstructed, reconstructed message. If it's very different from what you see, then you know that you're making a mistake, and you can feed that information back into your neural network. Now, the interesting part of this model is also that there is a particular constraint on this model, and namely, if you permute the users at the input side, you don't want the result to change, because these users, again, like in the graph neural net, these users are sort of permutation. The ordering is arbitrary in which you treat them in your computer. So you need to build a model that respects this arbitrariness in this ordering. And so, you can think of that as an equivariance sort of property, which says if I first if I have a channel and I permute the channels and then I send it through my neural network, that should be the same as first sending it through my neural network and then permuting the users around. I should get the same result. Okay, and the trick is that you need a particular kind of neural net, a graph neural net, in this case a transformer, to respect that sort of permutation invariance. Okay, so okay, I'm going to skip through this a little bit. So it's again an REM type of architecture, and there's here's this component which has this forward channel, and there's also this component which is actually a big transformer block to treat equivariance under all of these users. But in the end, you do a prediction, you backpropagate through the whole thing in order to get good at reconstruction. So we have some results that show that this actually works very well. I wanted to go through two more examples. The other one is one that we looked at, which is sort of optimization. So now the idea is, can we also do this amortization, but then for optimization problems? So I already discussed the sort of traveling salesman's problem, so what I'll turn it into the traveling scientist problem. So you need to find a path through all of these posters and end up at the coffee corner at some point in time. Right, and so the input that goes into your neural network are positions, where are all these posters located, right? And you want to find the path that travels the shortest distance if you go through these things that you're interested in. So we call that a policy. So the policy basically tells you where to go next when you've sort of visited these posters. What poster should you visit next? Now, of course, that's a TSP problem. Again, the input nodes, the cities or the posters, they are an unordered set. There's no ordering in it. And so we should think of this again as a graph, and we should sort of treat any neural network that we run on this basically as either a graph neural net or a deep set or transformer or one of these networks that respects this permutation variance. Now again, without going into the details, the method works as follows. You first take all the information, all the positions of the cities, you push them through your encoder, which is a multi-head attention network or a transformer. Then you get embeddings for each one of these cities, and then you sum them up to get sort of an embedding for the entire graph. So that's your encoder. Is amortized, right? Because you train this on many examples. Maybe that's the most important thing. So you train this on many examples of traveling salesman's problems, so you can train a good encoder. And then the decoder or the policy works as follows. There's this policy that looks at these embedding vectors. It then predicts what is the best city to visit next. You go to that city, you mask that city off the list, it's gone, and then you do a recomputation, and then your policy picks the next one off the list that would be best, right? So here the idea is that by doing this amortization, by looking at many similar problems, you can train this policy. Now this is not as good as running one of these really strong sort of traveling salesman's problems solvers, but I would imagine that in the future, when we combine these things, we can get the best of both worlds, especially when you have to do it quickly, right? If you're in a vehicle routing problem and suddenly the road situation changes, you may not want to solve the entire problem again. You might just want a policy that sort of quickly reroutes you to to go and find a sort of a path to the next sort of place to deliver your goods. Okay, and then the last thing I wanted to talk about is causality. I'll just skip this. This is work with Cindy and David and Rich. And this here is what we try to do, is we try to amortize causal discovery, right? And the idea is, let's say you have a bunch of particles, they fly around and they are exerting forces on each other. In this case, these forces can be asymmetric. A could influence B, but B could not influence A. And the idea is to try to solve this problem by looking at many of these problems at the same time, and then build an encoder that takes in a sequence and tries to predict, who influences who. So that's sort of a discrete random variable that tells you there's a link from here to here, there's a link from here to here, etc. And then once we have that link, we can then sort of simulate using that hypothesis for causal connections and see if that sort of, the simulator will do a good job at reconstructing the observations. And if not, then, clearly you've done something wrong and you update your model and you keep on going. Right? So the idea is to amortize this over many different problems. So instead of treating every problem separately, you're going to amortize this over many different instances. And the model works as follows. You have your input sequences. There's this encoder, which then predicts these sort of links, these causal links between these entities, these particles. Right? The encoder, because it has to be, again, permutation invariant, is a graph neural net. It takes in all of these particles. There's no particular ordering, so we make it a graph neural net, and that predicts these z's. And then the decoder takes in the sort of the positions x, the last positions x, and it takes in these z's that were predicted, and then it's basically either a simulator or again some kind of graph neural network that then sort of simulates how these particles would evolve under this sort of inferred causal relationships. So you get future trajectories, and then you can basically compare these trajectories with what you're really seeing and then optimize this model. Now, there's a lot of things we sort of researched in this case. So if you look at the training size, clearly these models will do better and better and better when you increase the training size. And that's what we show here. These are different versions of the same model, but the most important thing is you can get almost perfect if you observe all the particles and if you have enough data to train off. You can do, and that can be a lot better than if you would do it one by one. We've even tried to work with confounders. So let's say there is dark matter in this problem. There's particular particles that we never observe. How would they influence? You only observe them because they influence the particles that you do observe, right? Can you use this idea to infer something about the confounder and how it influenced these other ones? Now that's a much harder problem, and I think we have state of the art, but it's still not perfect. But this is a super interesting problem to look at, I think. Okay, so then to conclude, I think, yeah, 1 minute to go. So to conclude, I think that most people by now agree, well, actually that's not entirely true. Many people believe that we will need generative model and causal modeling to reach, sort of human level intelligence. And the idea is, the reason is that we all believe that we are far more flexible and robust in the way that we learn. We can learn from very few examples. We can sort of, we can generalize into new domains much better than these deep neural networks or these purely discriminative driven methods. Now, there's another class of people that think that by just scaling up deep learning to more and more data, we can also reach that point. And of course, I don't know the answer to that, and it will be very interesting to see, what is, who will sort of, who will prove to be right. But then, of course, one day you look at GPT-3 and you think, oh God, this might actually scale all the way, without doing anything sophisticated, but just statistical modeling. Okay, so I think the encoder decoder framework is very interesting. It's very similar to forward and inverse modeling in the sciences. It's a very general framework to look at sort of unsupervised learning. And I've discussed 2 design principles, amortization and augmentation in this context. And there's we've looked now at a lot of problems that can benefit from these design principles. And in this talk, I've looked at image analysis and time sequence analysis and communication, or wireless communication theory, combinatorial optimization, and causal inference. Thank you very much.
Thank you, Max, for this great talk. I'm going to take away the sharing so I can show people where to ask questions. So in your app, there is this button here. There's a chat down there. Don't click on that chat. Click on this. And then there's a Q&A here. There's already some questions there. The interface might look different for you, but you need to go into the individual item within the talk to ask the Q&A. And there's 2 questions there already. And I'll start with those. You can also upvote these questions. You can't downvote, but I'll sort of look at the most upvoted questions first. So Max, the first question is, what do you think is the reason that VAEs fail to detect out of distribution data?
Yeah, now that's a very deep and complicated question. I think it's not just VAEs. I think it's, people have tried, to model basically generative models or densities on, on the latent variables of some kind of VAE or other structure, and somehow, let's say if you train a deep neural net on one data set, and you look at let's say the latent representation of the data, and now you say, okay, now let's look at another data set. It's not necessarily true that that data will project in that latent space in a low probability regime. It can actually project right in the middle where the high probabilities are. There's a couple of papers. One is by Eric Nalisnik, and I think UIT and some other people on that paper that sort of study this phenomenon. I'm not an expert in it. I don't think it has anything to do with the VAE, but I think it has something to do with the structure of deep learning systems. That somehow, if you take a particular data set and you push it through that neural network, then they will end up in high probability regions where there's a lot of where the probability of finding a latent variable for the data set that you're looking at is also very high.
Okay, great, thanks. The next question, and this is already the last question that there is currently, so please do add questions. The question is there a meaningful link between the word amortization here and in computational complexity? That is there some large quantity being paid in one go and then recovered in small increments?
Yeah, I think that's true, right? Because and certainly in computation, but also perhaps in sort of so the idea is that if let's say you would do inference per instance, right? So you take a particular data point and you would then have to do run an inference algorithm for that particular data point. You have to run mean field inference, let's say, or belief propagation for that particular data point, right? And you have to do it again and again and again, even though the next data point might be very, very similar to the previous data point. You've sort of done all the computation already. You're going to do the computation again. So what the amortization principle says is that, well, why don't you train a network on all of that data so that at least you'll get a good initialization, right? So you can sort of say, so that would look at, what inference answers you would get for data points in this regime. And then you can do that fast, that part, because it's sort of inside a neural net. And then you execute that, and then you get a pretty good answer. There's still what's called an amortization gap, which is, it's not the perfect answer, but then you can run initializing at that point for a few extra iterations in order to get to the best possible answer. That's actually what we did for this causal inference, this amortized causal inference as well. So we often start with the amortized model, and then we do a couple of iterations on the decoder, basically optimizing over the decoder to find the best possible solution.
Yeah, I think also in the combinatorial optimization, learning a combinatorial TSP solver, right? You take a lot of instances and you learn that solver, and then you can actually quickly solve a new instance without actually spending a lot of compute on that.
Yes.
So I think that's another way in which it amortizes.
Yeah, absolutely. Yeah. So one is learning to optimize, one is learning to infer, learning to learn. They are sort of all optimization problems of some kind, I would say. Yeah, so but it's also interesting that they can't quite reach the same performance as a dedicated solver. So I think in the end, a hybrid system will work best, where you take the best of both worlds in some sense.
Now I'm somewhat confused. There is a question in the Zoom chat. I thought that is disabled, but I will read it. Is this model and technique applicable on multi-level data? What's the best way to estimate uncertainty in multi-level image data sets?
What precisely is multi-level data? I'm not sure what that is actually. Multi-level image data set. So I'm sorry, I don't know what a multi-level data is.
Okay, maybe we can get the question asker ask in more detail. Maybe I'll ask a question in between myself. So yeah, I'm talking about the learned TSP optimizers. So the way you amortize it is that you actually directly learn a probability. Okay, what city should I go next to? So you basically learn the entire TSP solver.
Yeah.
And in the end, you don't actually use any piece anymore of any traditional combinatorial solver. And you also mentioned that, well, that might not be quite competitive with these search algorithms, but it's really good in terms of generalization and so on. And I fully agree with that. What I do want to ask about is, do you think there's also virtue in trying to actually improve the original classical TSP solvers using machine learning, for example, by actually just controlling the hyperparameters and so on?
Totally agree.
There is this field of just optimizing basically hyperparameter tuning. It's called algorithm configuration, where you just optimize them offline to just optimize hyperparameters. But that's sort of boring, but you can also go online to actually do online tuning and online control. I personally think that's actually a really rich field that could be an alternative option to combine the best of both worlds. And I was wondering about your thoughts there.
No, absolutely. And we are definitely also thinking in that direction. So there's a whole spectrum. So again, like the first slide, there's a spectrum on one side where you just do only the classical algorithm. On the other side, you completely learn everything, right? But then there is many shades of gray in the middle. So you can go stay very close to a classical algorithm, but basically fine tune the hyperparameters, or even do this online, as you say, sort of a dynamic adaptation of your hyperparameters. Or you can go slightly more to the other side, where you would have sort of a learned policy, but the learned policy would maybe able to call a sort of a classical optimizer in order to compute something for it, right? Which would be slightly more to the other side. Or you could have an algorithm which would basically suggest, let's say in an evolutionary algorithm, it could suggest moves, or change choose the population or something like that, right? So there's many shades of gray in the middle of that, but I agree that's a very rich field to explore, and I think it also depends a lot on what you want to do with it. So if you really want just one solution for one problem, it doesn't make a lot of sense to do this. But if you're in a situation like, as I said, in the vehicle routing, where the situation dynamically changes, right? There might be the traffic situation might change, or I don't know, all sorts of things might happen, and then having this policy that was sort of quickly sort of generate solutions for you without having to resolve the problem again is also very useful.
Okay, thanks, great. Yes, my app was stuck with 2 questions, but now actually I reloaded and there's 7 questions. So there's lots of questions going on. I'll quickly do this clarification of the Zoom question. Multi-level maps input X to binary vectors Y label, e.g. scene image contains search, beach tree, human, etc. So with that in mind, what's the best way to estimate uncertainty in multi-level image dataset? If you want to skip, we'll skip.
Yeah, I don't think it sort of applies very much to what I was talking about, in the sense that I wasn't really talking about uncertainty estimation in the first place, although sort of probabilities are a side effect of it.
Right. There's lots of other questions with lots of upvotes, so we'll go there. Next one, the presented models are all data hungry models. Can you discuss how we can apply these models, especially the causal models, to industrial problems where the data sets are not as big as the ones here?
Yeah, so actually one motivation for doing this is to make these models less data hungry, right? So if you do a full deep learning solution or a full learning solution, you will need a lot of data. But by using more of the sort of inductive bias, or the prior knowledge, or the generative knowledge, or the measurement knowledge, whatever you have of the model, and infusing that into the model, you can learn a lot faster, right? And so, and with faster, I mean you can learn with fewer data points. So it's precisely this idea that by combining sort of signal processing solutions or engineering solutions with learn solutions, that you will be able to sort of go over this entire spectrum from very data hungry, which is full deep learning, to no data necessary at all, which would be just doing inference in a generative model.
Great. And one sort of related question. Thanks for the great talk. Can you share some insights on the complexity of your methods? Do they come with an overhead, or are you just overall safe because you need less data?
Well, there is the overhead in the sense that you have to learn your model. So so there's an offline phase where you have to generate data and learn your models, right? But once you have them at the inference phase or execution phase, right, you can actually be a lot faster, because think if you would have to resolve a TSP every time, versus you could initialize it really well and then maybe change it only a little bit. That will be a lot faster, but that's the amortization in some sense. So you pay in the beginning by learning, but you sort of you benefit at the inference or execution time.
Mm-hmm. Good. Then there's 2 related questions. The first quicker one is, what is the relationship with reinforcement learning? And a related one that has lots of upvotes is, where did it go? A number of the things you said reminded me of attempts at relational reinforcement learning in the past. Those have not gone super far as I know. Why would this be different for deep neural networks?
Okay, so I don't know about relational reinforcement learning, I'm afraid, but there is certainly a reinforcement learning element in some of these things. So it depends on if you can actually generate labeled examples. Like for the MRI case, there's no reinforcement learning, because you can just you can just create pairs. But for the TSP problem, that will actually map to a reinforcement learning problem, because there's only this thing like a reward, which in the end tells you how good is your actual solution. You can measure it, and so you can then backpropagate that into your policy and improving your policy. But that certainly isn't a supervised learning problem. That is a reinforcement problem. So it's very good to point out that this idea of amortization and augmentation can be applied both to supervised learning problems as well as to reinforcement learning problems. Yeah, I'm sorry that I don't know about relational reinforcement learning, but.
Okay, we'll go to the next question, which also has quite a few votes. If I have a setting where the background knowledge should be a hard constraint on the behavior of the model, like traffic rules for a self-driving car, do you see a place for that in this
Yeah,
framework?
well, that's a very interesting point, actually. So, so how would you incorporate hard constraints? And I would say that's external knowledge in some sense, right? So it's much harder to say, let me just generate a huge data set and then have to observe that certain combinations never happen. And since neural networks are sort of soft functions, smooth functions, they might make that mistake. So if you can incorporate that as prior knowledge or sort of external input into the neural net, then that would actually be super useful. So for instance, I can imagine that in this reconstruction, in these amortized reconstruction algorithms, if you would get a reconstruction that's false, then you could sort of raise a flag and say, this is very bad. You sort of violated one of the constraints, and you have violated it by this much, and then you feed that into your algorithm again, right? And then it will very quickly learn that it should not go in those regimes. So in fact, it's precisely, I mean, in some sense, you can think of these data forcing terms also as sort of soft constraints. So you can add all sorts of other constraints and make them, I would say, soften them a little bit, but just maybe increase the softness of it or decrease the softness of it, so that in the end it will really satisfy all of these constraints.
Mm-hmm. And what if you had an algorithm that actually guarantees safety? Could you then combine that somehow with a deep neural network?
Yeah, that's an interesting question. You need to make sure that your neural network doesn't screw it up, and I'm not quite sure how precisely so you would have to detect that it would go into a regime where it is no longer safe, and so that you could then shut off your neural network, right? You could sort of accept a correction by your neural net unless it violates some of these sort of safety margins, and then you would just go with your sort of safe classical solution. That would be another way to hybridize sort of algorithms.
Okay, excellent. We are 2 minutes over, and we're actually also at the end of the questions, so that's perfect timing. Thank you very much for that, Max. Thank you for an excellent talk, and yeah, I'm looking forward to seeing more along those lines.
Thank you very much, Frank.
Thank
Bye-bye.
you.